So we're going to do a power series example. So we're going to consider this power series that's already written out for us. So 1 minus 1/2 times x minus 2, and you can think about that as being like to an invisible 1 power, 1/4, 2 squared, x minus 2 to the second power, minus 1/8, there's a 2 cubed, x minus 2 to the third power. So a couple things we notice that it's alternating. We've got 1/2 to some power, and we've got this x minus 2 raised to the same power. So if we look at this, we can identify a first term. And we also know that we have this a value, this distance that we are off of 0, this minus 2. So in this situation, we're going to have a is equal to 2. And if I list my coefficients, I'll notice c sub 0 is 1, c sub 1 is negative 1/2, c sub 2 positive 1/4, c sub 3 negative 1/8, and that list can keep going. I can also determine my constant ratio by taking any term and dividing it by its preceding term. So in this case, when I do that division, simplify that, my constant ratio and so again, if I take any one of these terms and I divide it by the preceding term, okay, I'm going to end up with my constant ratio. Let me get those out of there. My constant ratio will be negative x minus 2/2. Okay, so this is a geometric series because we can determine that constant ratio. We know it's a geometric series. And if that ratio, if I say, hey, I want to make sure this converges, well, geometric series are convergent when the ratio is less than 1. So what I can say that I know is that this will converge for any situation where that ratio is less than 1. So I'm going to say x minus 2/2. I'm going to say, well, as long as that ratio is less than 1, I know this is convergent. And I can throw the negative away because negating something and then you put it in the absolute value bars, it's going to turn it positive again. So if I look at simplifying this expression I've created, that would be -1 less than x minus 2/2 less than 1. -2 less than x minus 2 less than 2. Add the 2 to both sides. I've got 0 is less than x is less than 4. So as long as my x value is between 0 and 4, I know that this geometric power series is going to converge. And the sum of a convergent geometric series is always set up as that first term divided by 1 minus the constant ratio. So my sum of a convergent geometric series is the first term over 1 minus that ratio. Okay? So my first term, scrolling back up, my first term is 1, and my ratio is negative the quantity x minus 2 divided by 2. All right, so the sum of my series is 1 over 1 minus negative x over 2 over 2, which simplifies to 2 over x. So what we have just said here is that this series that we started with, the sum of this series will be equal to this value 2 over x. So I'm going to rewrite that here. I'm going to say, okay, well, 2 over x is equal to, and my series, my list of terms is 1 minus, we had 1/2 x minus 2, so x minus 2 over 2 plus 1/4 x minus 2 squared over 4 minus 1/8, that's x minus 2 cubed over 8, plus some -1 over 2 to the n, x minus 2 to the n, right? And going on infinitely here. So this infinite sum is going to converge to 2 over x, but it's very important we notice this is only for x values that are between 0 and 4, only when x is between 0 and 4. So some polynomials that could approximate this, p sub 0 of x, that would be 1. P sub 1 of x would be my first two terms, which is 1 minus 1/2 x minus 2, which of course simplifies to 2 minus x over 2. And p sub 2 of x would be 1 minus 1/2 x minus 2 plus 1/4 x minus 2 squared, and that simplifies to 3 minus 3/2 x plus 1/4 x squared. Okay, so what we are saying here is as I put more terms in this polynomial, for any x value that's between 0 and 4, I'm going to be able to get a close approximation to the sum of the series. All right, so this, as these terms, as I have more and more and more of them, the curve of that polynomial is going to match this rational function, y equals 2 over x. And so to try and cement that idea, I've brought this graphic in. And what this is saying is that, as long as my x values are between 0 and 4, I can approximate this curve, y equals 2 over x, some rational function, with a polynomial, right? And so as my polynomial, as I add more terms from this power series to my polynomial, that polynomial is going to start to match that blue curve. And if you look at the yellow curve here, which was my quadratic polynomial, you'll see that this yellow curve is matching up nicely, or more nicely than the green or the red one we have there, as it has more terms. And so I could continue making this list up above. I could say p sub 3 of x, and I would get a curve that matches it even better in that region.